Hello, we are Ana Karen, Raul, Miranda, and Erica, and today we are going to be presenting our project, which is titled 3D Modeling of Blood Flow in a Simulated Abdominal Aortic Aneurysm. So for the project design that we chose, we started off by selecting the parameters of interest, which includes primarily the geometry of the aneurysm, which will be explained later on, the wall shear stress, abdominal flow patterns, as well as the arterial wall rupture. And we continued on with the modeling of our aneurysm in order to look into the interaction of the blood flow dynamics as well as the wall mechanics of the vessel, so that we could predict the mechanical behaviors of this aneurysm in order to predict a rupture, which as a biomechanical consideration is the mechanical failure of the wall. And posteriorly, we went on to the materials, methods, and results, in which we gave a detailed information about the studies that we conducted. And overall, we based this project on literature which is taken from a medical paper of conducted studies of CFD analysis of the modeling of abdominal aortic aneurysm. Next slide, please. Okay, so first of all, an abdominal aortic aneurysm is a pathological enlargement of the abdominal aorta, which we know that bifurcates into the right and left common. Next slide, please. So for the geometry parameters, healthy abdominal aortic diameters are usually around 2 centimeters and have a wall thickness of around 1.5 millimeters. And when there is an aneurysm, the vessel dilates and it can expand up to 9 centimeters. So according to this study, the maximum diameter of an aneurysm is 5 centimeters. Nonetheless, there is a 23% rupture with a diameter that is less than these 5 centimeters. So it is very important to mention that the biomechanical based approach that we are proposing by analyzing the flow of blood with different viscosities in these aortic abdominal aneurysms may be superior to this commonly used maximum diameter criterion.
Now for the materials and methods, we focus on different factors such as the geometry, which consists of the 3D model of an abdominal aortic aneurysm. This figure was constructed in SolidWorks. The simulation setup that consists of different parameters, boundary conditions, and initial conditions for the studies realized. One of them is the CFD, which analyzes the biomechanical behavior of tissue stress and blood flow hemodynamic, and the FE analysis to calculate the abdominal aortic aneurysm wall stresses. For the geometry of our AAA, it has the following measurements. On the figure on the right, we can observe each of the measurements and the final geometry of our AAA. For the CFD analysis, we had to establish boundary conditions which consist of blood viscosity of 0.0035. The inlet velocity was considered of 0.28, and we considered the outlet pressure as the atmospheric pressure, which has a value of 101,325 pascals. It's important to mention that we consider the blood flow through the aorta is incompressible and laminar. Also, it was considered that the fluid was a non-Newtonian, and the aortic wall assumed to be no-slip and rigid. We simulated the flow as a steady-state simulation.
Now in the results, we have, we did the state, we used SolidWorks to run the simulations, and we are interested in calculating the pressure, the pressure distribution, the blood flow patterns, the velocity distribution, and the wall shear stress distribution and values. So first we see here the velocity cut plot, and we see that at the start it has an average velocity at the inlet and all through the aorta, and then we get to the aortic aneurysm, the velocity decreases. Then as the aneurysm ends, it goes up again, and when it divides into the iliac arteries, the velocity increases. Here in the pressure cut plot, we see that the velocity, the pressure of the pressure inside the aortic aneurysm and in the aorta is significantly higher than at the end of the at the beginning of the iliac arteries. This is because of the reduced area and increased velocity. Next, we see the shear stress cut plot, and here we see that the shear stress is distributed with higher shear stress at the beginning and end of the aortic aneurysm, and less shear stress in the middle walls of the aortic aneurysm. And this is because of the blood flow pattern that we will see in the next slide. We see here a concentrated spot where the blood hits the aortic wall of the aneurysm. And here we see that basically no blood is flowing through this wall. And we see here, we see in the blood flow pattern, the demonstration of this, we see that it begins with a laminar flow, and then because of the geometry pattern changes, and it becomes a bit turbulent here. We see that basically no blood is flowing through this part of the aortic aneurysm, and we see here a bit of the velocity in the colors. We see here it decreases and how it increases at the iliac arteries. But what's most interesting is this turbulent flow. We see how it hits here with a higher velocity in this part of the aneurysm, and this blood flow pattern is pretty interesting and dangerous because this reduced velocity and this pattern increases the probability of a thrombus in this parts because of a stagnated blood flow. Here we see the animation of blood flow. We see how it begins with higher velocity, and this turbulent side is fairly slow, basically stagnated flow is there. We did this study again, but with a high viscosity now, and we see here, and we will see in the next slides, the comparison between the normal and the high viscosity. The normal viscosity was with 49% of the hematocrit, and the high viscosity, we increased the hematocrit by 4%. We see that the values of velocity are didn't change a lot, and we see that the patterns are basically the same. We see a bit of change in the pressure cut plot, but it's basically not changing. And what's most interesting in the cut plot, in the pressure cut plot, is the distribution of the pressure. We see here is a lower pressure, and here's a higher pressure. In the shear stress, we see that, as we expected, the model with the higher viscosity increased the shear stress, the wall shear stress, and we see here, but the pattern is basically the same. We see a concentrated point of shear stress here at the end of the aneurysm, where we saw in the blood flow, as we will see here again, where it all clashes and crashes in the aortic wall of the aneurysm. The blood flow pattern is basically changed, just with a bit of less velocity in the part of the aneurysm. And what we see here again, the stagnated blood flow that is resulted of the geometry. That is result of the geometry.
So now talking about the discussion of the study, we have these main equations, which is the first one, flow velocity, that states that velocity is equal to flow over area. Our flow is with the Possehl's equation, which states that flow is laminar and parabolic, with higher vectors on the middle of the aorta and smaller vectors at the edges. So here we have new variables, which are the blood viscosity and the pressure drops. Also, the area, we have the geometry of the aorta is circular, so we have that the area will be P times the square radius. The wall shear stress equation relates the viscosity of the fluid, the velocity, and its diameter. And finally, the Reynolds number tells us if our flow is laminar or turbulent, and this will depend on the blood viscosity and the density. About the velocity analysis, we found out that when flow increases, velocity also increases, and when the area decreases, velocity increases. And here we can see that, for example, when in the iliac arteries, we can see that area became smaller and therefore our velocity vectors were higher. And at the aneurysm sac, the area was bigger and the velocity vectors were smaller. And the velocity streamlines have asymmetric patterns inside the aneurysm, and its flow has a negative direction. Here we can see that when flow bounces the wall, it bounces upwards, creating the negative pattern. And this pattern provides information about possible consequences, such as thrombus formation and enlargement of the aneurysm. Then pressure analysis, we have that Bernoulli's principle states that pressure exerted by a flow is reduced when the velocity of the flow increases. And on the other hand, when our velocity is reduced, the pressure increases. The increase of pressure inside the aneurysm over here promotes the increment of the AA diameter. And both of these variables are directly proportional. So if our diameter increases, the pressure also increases. And we can see in the pressure cut plot that the highest pressure values were at the aneurysm sac. About wall shear stress analysis, higher values of shear stress are due to the location where blood flow jet has an impact on the aneurysmal sac, which is over here. And it can be here translated in the wall shear stress plot. This is provoked by the proximal neck angle of the AAA torosity, which is this one. The pattern of vortex inside the aneurysm sac is greater with a greater angular neck, and the velocity field appears to be more intensive near the middle of the aorta. So here, this is the vortex created inside the aneurysm. So when we have a greater necking of the aorta, our flow first is laminar. Then the jet hits the wall in this part, creating greater wall shear stresses, which will be these ones. And the flow will bounce back, creating the negative flow and creating the possible thrombus. And after that, flow will be restored through the end of the aneurysm and to the iliac arteries. So concluding the study of our final project, blood flow generates unsteady forces on vessel walls that causes deformation of these walls. And at the same time, these deformations influence blood flow patterns. The conduction of CFD modeling of abdominal aortic aneurysms proves to be an insightful approach for the clinical setting.
When carrying out the biomechanical analysis of the AAA, the variables that have been observed in the different results are fundamental to help us predict the risk of rupture. Also, this demonstration of a biomechanics-based approach to predicting AAA rupture may prove to be superior to the widely and currently used maximum diameter criterion.
So by carefully considering the biomechanics of AAAs, there could be a case-specific prediction of potential ruptures, which could significantly improve the clinical management of patients with AAAs. Nevertheless, it's important to mention that this study in particular has limitations, primarily because it was ran under steady-state fluid flow, while in real conditions, blood flow is transient and pulsatile. But given the current literature, this is a project worthy of continuous investigation for the development of more precise models on how to predict and manage patients with abdominal aortic aneurysms.